let's look at some other properties of the less than relation. So this is not so much about the less than relation or how to use pattern matching on it, even though that's also useful, but to introduce you to some of these concepts that I used. So the first one that's important is the property of being propositional. So this is defined in the standard library, and we can see that a type A is propositional if for every two elements A and B of A is equal to B. So it's propositional in the sense that there is no actual computational content in this type really. All the proofs of it are equal. So it's more important if it is inhabited or not. So if you're very classically minded, a propositional type is either empty or the unit type, right? That's not quite true constructively, but that's one way to think of it. So we think of these things as really representing logical things rather than, say, the natural numbers where there's lots of different inhabitants, right? So the two most concrete typical propositional types are, of course, the empty type and the unit type. So the empty type because there are no elements in it, and the unit type because there is exactly one element in it. Okay, but how do we prove this for the smaller than relation on the natural numbers? So here a priori it looks like we have two constructors, right? So that doesn't look very propositional, but actually they target different indices in this type. So let's see if we can prove it. So what we have to prove is that given two proofs A and B that n is smaller than m, then A should be the same as B. Right, so let's take two proofs. I'm going to call them P and Q instead. So think of them as proofs. And now I have to show that P equals Q. Right. Okay, and how do I do that? Well, I do it like I always do for things defined by data. I pattern match on it. So let's pattern match on P first. They're both of the same type, so it doesn't really matter which one we do first, right? And we see that P could either be the first constructor or the second constructor. So if P is the first constructor, that has refined the types of the things involved. So now the type of Q has changed to 0 being smaller than m. And if I pattern match on Q, I'm going to see that there's only one possible constructor of that type, which is the same one as for P. Right? So now I have to show that these two things are equal, which I can easily do. And similarly here, by learning that the first constructor was one of these s less than s, then I know that I've refined the type of Q to be suc m less than suc n, which again, if I pattern match on Q, I learn that there's only one way to be that. It's if it's the second constructor. So now again, I have to show that something which is the same on both sides, and then some things are equal. So that's a job for Kong of s smaller or equal to s of something. Right. Okay, and I have to show that P equals Q, but I can do that with a recursive call. Right. Okay, so as perhaps expected, this thing really is a proposition in the sense that the only information in it is if n is smaller than m or not. It's not more than one way that n can be smaller than m. And here's another important property that we care a lot about. It's the property of being decidable. And you can go and look in the standard library to see how this is defined. And nowadays it's defined a bit strangely. So let me go back and explain it myself instead. So first of all, what are we saying? We're saying that for n and m, it is decidable if n is smaller than m or not. So the way to think about this type is that it's a type with two ways to construct things in it. You could either say yes, this is true, in which case you have to give proof that n is smaller than m, or you have to say no, it is not the case that n is smaller than m, in which case you have to give proof that of the negation of the statement. Right? So by looking at one of these, we can tell if it's the case or not. Right? So it's decidable. We can decide which one it is. Okay, and now how do we prove this? Well, now we have no choice but to look at the n and the m, right? And because the thing we're trying to prove in the end is kind of biased on the first argument, it makes sense to first look at the first argument. So I'm going to pattern match on the n. Right, see that the n is either 0 or a successor. If it is a 0, then, well, we have to decide if 0 is smaller than or equal to m or not. But we have a constructor for this, so we know that this is always going to be the case. So I'm going to say yes, that's one of the constructors for the deck type. Yes, it is the case that 0 is smaller than m. And now here, I have to give a proof that 0 is smaller than m. Can't just say that it's so without giving some evidence. But that proof itself is this one constructor doing exactly this, right? Okay, what about here? Well, here we have to see if suc n is smaller than m, but we don't know if this is the case yet. It really depends on what m is, right? So let's pattern match on the m. So you see that the m is either 0 or a successor. If it's 0, then we have to show that suc n, we have to decide if suc n is smaller than 0 or not. Well, I know that that is not the case. I'm going to say no. And then here, I have to give a proof that suc n smaller than 0 leads to false, right? So this is not the case. Well, let's do that. It's going to be a lambda something. Okay. And now what do I have? Here I have an x which says that suc n is smaller or equal to 0. Well, I can't pattern match on this here, but if I pattern match by hand, I'm claiming that this is impossible. There is no such x. Right, and Agda is happy about that. So here's an absurd lambda where I'm saying this argument is impossible. Okay, what about this one? So here we have to decide if suc n is smaller than or equal to suc m. And this really depends on if what n and m are, right? So what you typically want to do in this situation is you want to do a recursive call, which is this, right? So that's making me decide if n is smaller than m or not. And then I want to look at this result and do different things depending on if this is true or not. So that's exactly the job of a vid, right? So I write vid, I write the expression I want to look at, which in this case is a recursive call. I go to the next line, I write dot dot dot, I write a vertical bar, and I write something which I'm going to pattern match in a second. So I'm just going to call it xx. Because now I have this extra assumption that xx is the result of running this thing. So if I pattern match an xs, okay, it's doing it a new way, so I'm going to do it by hand. It's either going to say yes, n is smaller equal to m, or it is going to say no, n is not smaller equal to m. Okay, so in this case, I have a proof that n is smaller or equal to m, in which case it should be the case that if I stick a suc on both sides, this is still the case. Right? So this is yes of something. And what it is something, here I have to show that the suc is smaller than a suc. That's exactly what this constructor does for me. And then I have the proof I want here. Right. Okay, so in this case, I know that n is not smaller than or equal to m. That's this proof that I have here. So then it's also not going to be the case that if I stick a suc on both sides, this happens, right? So I'm going to claim that this is a no. Okay, and now here I have to give a proof that if this is the case, then bottom, right? So I'm going to do that with a lambda, and I want my lambda to be able to pattern match, so I'm going to put some braces like this in it. So in a normal lambda you can't pattern match, but if you put these curly braces around the thing, then you can also pattern match in the lambda. It's sometimes useful. So the one thing you can't do if you do this is a recursive call, right? Because you haven't named the function. but you can still pattern match on it. So now what do we have? I have a x which says that suc_n is smaller than suc_m. So if I pattern match on that x, I learn that there's only one thing it could be. It has to be this constructor applied to some x. Rename that x a p. Okay. But now, on the one hand, I know that p says that n is smaller than m, and this thing says that n is not smaller than m. So if I take that thing and I apply it to p, then I get something in the empty type, right? Which is what I wanted. Okay, so we see that with a little bit of width trickery, which might take some while getting used to, we could actually decide for n and m if n is smaller than m or not, which is very useful when we are writing programs. So what have we learned? Well, we very carefully didn't go down the wrong path, but if you do, then this can be really painful. And when you have more choices like this, then it's starting to become more and more likely that you will go down the wrong path before you go down the right path. So I try to avoid that in these videos because I want to keep them as short as possible. But there's nothing wrong with taking stock and trying something else. And we've also seen how to use with to pattern match on extra data, such as this recursive call. It's kind of crucial for making progress here. Right? This also takes some time to getting used to.